Meteorites have been used to make some of the most important inferences about the composition of the Earth and the composition of the individual layers of the Earth, especially the mantle and the core. So what I want to do in this little video is review in a simple way the different kinds of meteorites and what they tell us. Broadly speaking, meteorites can be classified into one of three categories. We have things called the stony meteorites, and stony meteorites are stony. They are basically silicon oxygen compounds similar to rocks on Earth. On the other end of the spectrum, we have things called the iron meteorites. And iron meteorites, just like their name suggests, consist largely of metallic iron with a little bit of nickel alloyed into it. And then we have a smaller group, a rarer type of meteorite called a stony iron, and it's exactly what its name suggests. It's actually a mixture of the two. It's a meteorite that contains a lot of stony, rocky material, but it also contains some amount of pure iron as well. And so the question is, where do these come from and what can they tell us about the Earth? Well, remember, all meteorites are thought to represent pieces of planetary bodies that probably formed at about the same time the Earth did, but didn't survive as planets. So these are either small bodies or planetesimal sized bodies that for some reason collided with another object and broke into zillions of pieces. And it's those pieces then which actually fly through our atmosphere and land on Earth and we collect and call meteorites. So they all came from some other kind of body. And the question is, what kind of body did they come from? One of the most important types of meteorites is a type of stony meteorite called a carbonaceous chondrite. And a carbonaceous chondrite, the reason it's called carbonaceous is because it actually contains carbon compounds, so it couldn't have gotten very hot, is thought to represent meteorites that formed from bodies that represent simple condensates of the solar nebula. So the solar nebula, the dust that was condensing to form all the planets, right? That dust condensed to form a small body that never differentiated. It's got all the stuff that was originally in the nebula, and it's all in one place, and it hasn't separated into different components because it never got hot enough. These are the most primitive meteorites and are thought to represent the same stuff from which the Earth was made. So in a way, they have a composition that should resemble the bulk Earth composition, the composition of the Earth if you stirred together all the components of the mantle and the core and the crust and put it all together. So these carbonaceous chondrites are thought to have a composition that's similar to the bulk Earth, or rather the bulk Earth is thought to have a composition similar to carbonaceous chondrites. And so they're very useful for looking at the total amount of the elements that must exist in the total Earth. We have to know whether it's part of it. For example, the iron. Okay, the iron is obvious that's in a carbonaceous chondrite. There's a lot of iron in a carbonaceous chondrite. Well, it's not in the crust and it's not in the mantle, and so we can conclude therefore that it has to be in the core because the bulk Earth must have a composition similar to those of carbonaceous chondrites. Now, other main types of meteorites come from bodies that differentiated much like the Earth. So they're bodies that maybe were larger and got large and hot enough to where they formed a core and some kind of outer mantle-like body. And then these planetary objects again collided, broke into a million pieces, and so we have pieces of these differentiated bodies which can come from different parts of the body, right? We have some pieces which came literally from the core. So we have pieces of the cores of differentiated bodies, and these indeed look like iron. So these are what the iron meteorites are thought to come from. They're thought to come from fragments of the cores of differentiated Earth-like planetesimals that shattered and broke into a million pieces because they collided with something else. We also have stony iron meteorites, which are the rare ones that seem to have come from areas near the core mantle boundary of these planetesimals. So these things which have pieces of both the core and the deep mantle are what form these rare type of stony iron meteorites. And then we have lots of meteorites which are the stony meteorites, which appear to be pieces of the mantles of these of these differentiated bodies. Now, this is a little bit more complicated because, in fact, they don't exactly resemble what we think the mantle of the Earth looks like. But that's because these bodies might not exactly have been like the Earth, but nonetheless, they represent rocky material, iron poor material. They don't have iron metal in them. That probably came from the differentiated outer portions of these planetesimals after they differentiated. And these then represent the stony, differentiated stony meteorites. And when we look at those, they resemble in some ways the mantle of the Earth. When we look at the differentiated iron meteorites, they resemble and very closely resemble what we think the core of the Earth looks like. And when we look at the carbonaceous chondrites, we think that composition is very close to what the bulk Earth must look like.